Good morning, all. Welcome to the workshop. Welcome to the workshop for professional naval architects. We are delighted to begin today's session with a panel discussion on advances in marine structural modeling and analysis. It is my pleasure to introduce our esteemed panel chair for today's discussion, Dr. Manoj T. Isaac. Dr. Manoj T. Isaac is currently serving as an assistant professor in the Department of Ship Technology at Cochin University of Science and Technology. Prior to joining CUSAT, he worked as an assistant professor in the Department of Naval Architecture and Ocean Engineering at the Indian Maritime University, Visakhapatnam. He holds a bachelor's degree in civil engineering from the University of Kerala and a master's degree in ocean engineering from IIT Madras. He also served as a project officer in the Department of Ocean Engineering at IIT Madras and had worked as several prestigious projects sponsored by DRDO laboratories and other leading R&D organizations, including NPOL, DRDL, and NIOT. He received his PhD in Ocean and Naval Architecture Engineering from Memorial University of Newfoundland, Canada, where he also briefly worked as a postdoctoral fellow. His research interests span dynamic modeling of unmanned underwater vehicles, experimental hydrodynamics in controlled and uncontrolled environment, and the dynamics of offshore platforms. We are honored to have Dr. Manoj T. Isaac as the chair of today's panel discussion. Welcome to the dais, sir. We have 4 distinguished panel members representing extensive experience from both academia and industry. Our first panel member, Mr. Girish Menon, Technical Director and Managing Director of S&O Maritime Services. He is a naval architect, having graduated from the Department of Ship Technology in 1997. He has an extensive professional career spanning India and the Middle East with valuable experience at renowned organizations such as Cochin Shipyard and Albadi Daman. Currently, he heads a design consultancy firm, S&O Maritime Services, with offices in Ernakulam and Abu Dhabi. Over the course of his career, he has been involved in a wide range of activities, including ship design, shipbuilding, repair, and project management. May I request Mr. Girish Menon to kindly take your place on the dais. Our next panel member is Mr. Anish Kumar Menon, Operations Director at Capital Ship Solution. He holds a BTech degree in Naval Architecture and Shipbuilding and MTech in Computer-Aided Structural Analysis and Design from Department of Ship Technology, CUSAT. And he is currently pursuing his PhD at Department of Ship Technology. He has maintained a long-standing association with ShipTech, beginning as a student in the mid-1990s. With over 24 years of professional experience, he began his career in the software industry with TCS, gaining international exposure in India and Australia, before transitioning back to his core domain of naval architecture. He has since worked with leading design houses, shipyard in India, Singapore, and Japan, contributing to several high-profile projects. His major areas of involvement include FPSO conversions and new build, ship design, production engineering, and greenfield shipyard development. Currently, as Operation Director at Capital Ship Solutions India, he heads the engineering, survey, ship registration, and project management division from the Cochin office. We are pleased to have Mr. Anish Kumar Menon as part of today's panel discussion. Welcome to the dais, sir. I would like to introduce our next panel member, Mr. Nishu Kurup, Principal Engineering Advisor, Naval. He is an offshore and marine engineer with over 17 years of industry experience based in Houston, working across offshore oil and gas, floating offshore wind, deep sea mining, and advanced marine systems. He has led and contributed to several offshore projects, including serving as a lead fatigue engineer for the world's first semi-submersible offshore wind turbine, WindFloat. His expertise spans the areas of finite element analysis, hydrodynamics, risers and moorings, control system, digital twins, and physics-based numerical modeling. He holds a bachelor's degree in naval architecture from IIT Madras and a master's degree in ocean engineering from Texas A&M University. He currently serves as the Principal Engineering Advisor at Naval. We respectfully invite you to the dais, sir. Our fourth panel member is Ms. Amala Sebastian, Manager, FES Smart Engineering and Design Solution. She holds a BTech in Civil Engineering from MA College and an MTech in Computer Aided Structural Analysis and Design from CUSAT. She currently serves as a Manager, FEA at SETS, where she is handling finite element analysis for both defense and commercial projects. Welcome to the dais, ma'am. The dais is now open for the panel discussion. Over to the panel chair.
Good morning, everyone, and welcome to this second panel discussion on advances in marine structural modeling and analysis. We have four speakers for this morning. So the way we are going forward is like first we will have a brief presentation by each of the speakers and maybe 10 minutes. And then we'll go for the, so you can, if whatever questions you have, you can save it. We'll go for a discussion at the end of the session. Okay. So first I'll call first speaker for this morning is Mr. Girish Menon, a Technical Director and Managing Director of Ascendo Maritime Services. Over to you, sir.
Hello. Good morning, everyone. I hope I'm audible. Okay. So first of all, let me thank the organizers and the department for giving me an opportunity to speak in front of you in the department from where I graduated 28 years ago. So the topic for the day is advances in structural modeling and analysis and all. So I'll just give a brief about what I'm going to speak today, because I must first admit that I'm not really a structural engineer, and I'm actually heading the company where I'm supposed to do the evaluation of the designs made by my engineers, and dealing with the clients and dealing with the feedback from the from the uh, uh, from the clients, from the yards and all. So that my perspective will be, although as a company, we do a lot of activities like naval architecture, shipbuilding, and all those production support. But today's main focus will be on the structural engineering side. And I understand most of the audience are from students, except Shiva Prasad sir. So I think I will just give a brief on what is expected by the industry in terms of when we do the real modeling using the structural engineering. So structural engineering, as we look at it, it's something which we all industry uses, whether it's marine or a civil or automobile. But what is important about the marine structure is that it's a complexity in nature, because we are actually not a fixed structure. Mainly, although we have the fixed structures like the platforms or offshore windmills and all, but mostly the environment is flexible, the waves, wind, current. So the complexities, the environment is something which creates the interest, especially for the structural engineers. And the structure itself is very complex, and most importantly, it's a very capital intensive business. So the expenses are in millions or billions of dollars. So a small error or some carelessness or whatever we call it, it creates a big loss to the industry. So that's where we have to be careful when we do all these kind of analysis. So In the today's scenario, basically what we are doing is in the structural modeling, it's basically the FEA, finite element analysis. That's what we are more concentrating. And now it is what I see from the industries. We are more software oriented design. And of course, it's very easy, convenient, and yeah, less time consuming. So software is like ANSYS, Bentley, that's StatPro, something which we use in our company. Mostly ANSYS for the plate structures and the Bentley StatPro for stick model frames, beams and all. Other softwares like Abacus, Sesam, SAX, everything is also being used by many industries. But mostly we are working with the in a software environment. So the main the main focus, what we are looking at is the environment, what we do. In the process, yes, there are various steps as can be seen in the screen, like we do the modeling, we do the meshing and the load, we provide the boundary conditions and all those things. Then if you find out the results and the verify with the allowable results given by the various authorities or the courts or the societies, and we verify, check whether it's okay or not. This is something what's happening in in the process. I think that is something which can be explained more by the structural engineers who are present here. I'm not really going into detail, but what I'm going to talk about is how do we approach the process, or in a nutshell, because the thing starts with modeling. I would say the modeling side is something which is, although it time consuming depending upon the volume of or the structure, the size of the volume, but in principle, I would say that would be a much easier one, because we sometimes we are given the model and we just have to model it from the drawings. So only thing is we need to get it correct, with the connections or the welding, whatever is there. But we have sometimes we have the model and we have the drawing, we model it in any of the softwares. Sometimes we are not given the model. In that case, it's a bit critical because we have to start from scratch. But ultimately, the model is something which is starting point. And when we have a model like what is shown in the picture, it's like a job which we did for a barge global analysis. The entire barge is modeled, and then the process starts. It's completely we are modeling. But when it comes to specific requirements, like we did for pusher barge, where the tug is pushing a barge, where there is a connection, something called articouple, where the barge is connected to the tug. So all the loads are actually acting on this particular area. So the load on the barge as well as the tug connected through the articouple. So here the thing is, we are not modeling the entire vessel, but only a part of it. So as you see, the if you look at the stress pattern also, once it comes to the to the bulkheads, two or three bulkheads, we stop it. We don't do it. So we have to analyze in such a way that how up to what extent we need to model that one. So sometimes you model up to particular bulkhead, then you find there are more stress over deflection, then you go further. So that is a decision we have to take during the process. And then if there are some other things like installation of a crane on a particular location, or installation of some machineries like towing pin or shark jaws. So these things we do only on a part only. Then comes the meshing size. Meshing, what we do, of course, depending upon the complexity of the meshing, or or the area or the loads, there are types of mesh and size of mesh. I'm not an expert to go into the meshing details. But finally, what happens, we do the modeling, then you give the loads. Either the software provides a load, or sometime we calculate the load. There are a lot of codes and equations and the theories are behind that. Boundary condition is something which is really a very complex for me, because I've found some of my engineers are really not able to get it correctly, because ultimately, although we depend mostly on the softwares, it depends on how closely you can simulate that model close to the actual scenario. So unless you get it correctly, you will not get the result. So it's not that the structural engineer should be is like a software operator, but we have to have an idea on how do we simulate it properly so that it matches or meets the or it is similar or close to the real time scenario. Unless you don't get it correctly, the results will be wrong. And when it's normally happens to us also that people run the software, get the results, and print it out and give it to the client, and sometimes they point out it's not correct. So because most of the cases we work less software operator. So what I'm trying to explain here is that I always tell my engineers that once when you get a problem, try to visualize the structure in your mind, not in the software. Give the loads, give the boundary condition, everything in your mind, or how it operates, and try to simulate the entire scenario in your mind and understand the behavior of the structure, how it is going to behave in that particular condition. For example, if you have a plate and you're applying a load at the center, you know it's going to deflect at the center. So if you get a result which is opposite to that, you know there is something wrong. So similarly, it is possible from experience, from your knowledge, to at least have an idea, the pattern. And when you analyze, you get the results, you compare with that. And if it is matching, then we are almost there. Of course, the values we cannot validate, but at least we know that it is something happening in the right direction. So that's something which we should have an idea. And for that, what I'm always telling my engineers is that to visualize, because the problem what we face nowadays is it that mostly we get engineers directly from the colleges where they are not exposed to the industry, or they are not seeing the real situation. So they are just doing it from their whatever they think about it, and then they are not able to visualize what's happening. So I always tell my engineers everything, especially the aspiring engineers, you should have a kind of attitude to observe things around you, whatever structure, whether this hall or maybe a bridge or a shared workshop, how the structure is connected, how is the connections, how are the brackets, how are the bolting. You should have a look at all these structures wherever you go. If you're planning to become a structural engineer, yes, you should see these things. It's not that ships and offshore is our field. It's everything is engineering, and the theory is same. So I always tell even the bridges, even some of the shopping malls, for example, the roof structures are really really great. Especially not here, but when we go out in the other countries, the way it is constructed is really nice. It's really nice. It looks very simple. But most of the cases we find the design is over design, but when we go and see some structures, we find that it's very simple and very light. So that is where we should have an idea. So we should start looking around and see things around you and start applying it in your model. Then you get better results. That's what I can advise, especially for the new team. Uh, some of the projects where we have used is like the hinge structure of a split hopper barge, lifting analysis, cable baskets, silo where which is used to create the grouting, used for grouting the monopiles, uh, some tools where we use the FE models. So as the matter which is on the red is something which is more interesting to me, because I work with some yards, especially we have some sister concerns where we give the drawings and they construct it. We get the direct feedback, and most of the cases their main problem is, one is the way the structure is very heavy. Sometimes they don't get the material in the market. Sometimes the grade may not be available. So when a requirement comes to us, what we do is, if the yard is directly constructing it, yes, then what we do is we do a basic calculation and then ask them whether these are the materials we are trying to use in the model, and then check whether it is available in the market. And we get some feedback and we use that model, because nowadays uh, unlike in the olden days, everything is 3D model now. We don't create a 2D drawing. So everything is in 3D model, and then finally the output is taken directly from the model. So any change in the model after the everything is done, approved, then do a change not easy. It's a problem for the designer, problem for the approval authorities, and the biggest problem is for the yard and the owner, because it is time consuming and you lose at the cost, especially some material we have to export or import from the other countries is going to be costly. So that's the thing. So when we are doing a design, yes, please have a look at how the market is, or what the yard is looking for, what are the material availability, and try to get it as optimized as possible. Because people, engineers, generally what happens is that we tend to do safe way of dealing, because instead of getting say 20 let's put 25 plate, and then it's easy for you because there is no issue later on. And people don't realize 20 and 25, what's the difference, because people have not seen it actually. So uh, what we should realize is, we once you have that feel of how it look like 25 plate is something is very big actually, especially when it comes to the weight handling, how the construction is to be done by the people, use of craneage, the cost is very heavy. For example, the picture in the model, which this is something we did for a client in Europe. It's a monopile, wind offshore monopile sea fastening structure, which is used to transport the monopile, the pile for which is installed first on the seabed. It is transported and it is upended, like it is turned upside degree and lowered to the seabed. Our job was not to do the entire structure, but our job was to do the access, the blue color, the stairs, ladders, to approach the all the areas where there are maintenance required or some connections required. So although it looks very simple, it was very complicated because the structure itself was not fixed. There are flexibility, there are a lot of movements were there. So all these things should not touch each other. So we started doing it and we found, okay, it's not very simple. But finally, when we saw the real structure, actually, it was a very huge structure, actually. So if you look at the picture, the crane standing close to the thing, or the human being, the person who is standing there, it's really, it's a huge, it's about 40-meter high and about 30, 40-meter long. So when you look at the computer and when you look at the real structure, it's totally different. It's a big, big structure. So when we start putting things together, we found out that some of them are very heavy, some of them are very, very small. So my uh, my uh, my point is that yes, we have to follow the rules. We have to follow um, the principles, everything. First principle, experience, everything. Finally, what industry is looking for is a design which is optimum, lighter, which still can do the process, production friendly in terms of construction easiness, and of course, it serve the purpose. So theory is good, everything is good, but we have to have a practical approach. And for that, we need to have an exposure. So get the theories right, have the practical exposures, and use the relevant materials in the designs. And once you have it and you have a good design, and then that's what we should move forward. So that's what we are concentrating, and what's what I tell my engineers, and that's my advice to the young engineers who are aspiring to be the future designers in the industry. Thank you.
Thank you, Girish. Um, the next panel member we have is Mr. Kumar. He's the Operations Director at Capital Ship Solutions. He's a through and through naval architect. He holds BTech from here, did his master's, and currently pursuing his PhD. So over to you, Anish.
So, very good morning to everybody. And first, thank you all for coming down on a Saturday. I know it's a holiday, and still we got a sizable crowd over here. So, this particular topic, advances in marine structural modeling and analysis. So, when I got this advances in marine structural modeling, I was just thinking like our focus or our area of discussion should be like what is going to come, which we are not seeing. I just did some research, and based on the industry feedback, I put in some slides which indicate where the analysis is heading to. So currently, when we are talking about the structural analysis, we are talking about, we are analyzing the stress, and then it's like we have got tools which are capable of doing that, and you are just looking at the results and you're giving a solution. But there should be a holistic perspective. When we consider the entire life cycle of the vessel or any asset, as to when you start the basic design, when you move on to the production. So that integration is something which is not really happening at the moment, but that is what is going to be the future. So I'll just touch upon those kind of topics over here. And the detailed level of analysis, I will not be touching, because we have got eminent panelists over here and who has got more hands-on than me. So let me move on with this. Yeah, I hope it is readable for you. So mainly when we are talking about an analysis, it's more about a workflow. You are having the data. You are having. I'm just putting it into 4 different buckets where you are having softwares which are capable of doing multiple areas. Like you have got a general purpose FEA. I'll just start with the second bucket. So you got, most of you will be aware of, you have got ANSYS, FEMAP, SimCenter, which is mostly dealing with the physics, or you can do your nonlinear analysis. That is mostly for the structural engineers. But when you talk about a few people who are here who are into naval architecture, their core area will be like the second bucket, the third one, sorry. In fact, the hydrostatics and stability, where softwares like MaxF and GHS, it can do the stability based analysis, and it is more focusing on stability and hull optimization. But you should, as a naval architect also, or as a structural engineer, you should be understanding there is a link between both. It's not just doing the stability. Suppose you are having a loading condition which is extremely tough on your structure, like your shear force are quite high and then your bending moments are quite high, then you have got a structural problem over there. And then when you resolve the structural problem over there, you may end up in adding a weight to the vessel, and then it again comes back. So as you are aware of, there is a spiral. So where there is an interoperability, or there's an interrelation between these two. And next come the class and complaints. Like these days, we are not simply submitting our rule calculations or our analysis directly to the class, but we have got softwares which are capable of, whatever analysis you are doing, you can do it in the class proprietary software, where it will be easier for them to analyze and then approve your designs pretty faster. So there is a direct, when you have a single point of, it's called a single point of truth. You have a same model which the class is using, you are using, you will not have surprises. But I can see, even now also, when we submit simple things like, stability, you are giving a damage stability, you somehow manage your loading condition with your expertise, you get an approval. You get a marginal pass, then it comes back from the class saying that no, it's not passing. Then you are puzzled, what's happening, because you don't have a single model. So now the industry is coming to an integrated focus. That's where the first box comes in. Like you have an integrated design where same software or same database itself can handle all the way right from the initial design to production engineering. But till date, to be honest, there is no single software which can handle everything. So it's not a software related problem I'm saying, but a general approach where you are working on a single model. So just moving on, talking about FEMAP, off late the advances in FEMAP, you are having hex dominant meshing, which is more applicable when you are doing your bending related hull girder bending analysis and all. The hex model is easier. And then there is a better element quality. See, nowadays, when we are doing, whether it's CFD or FE, we are spending most of our time in making the software understand what we need. You have a model, you probably, you have been pretty fast in doing a modeling in Rhino or any modeling tool. But once you get to the meshing part, you're just cleaning up a certain area and then you're wasting your energy over there. So hopefully, by the time you guys, graduate, and you'll be having better tools, and then you will be focusing on the real engineering problems than in making the software understand what we are supposed to do. So that is where, these advances in FEMAP is helping. The meshing is getting automated. There is a lot of patches which is coming. there is no triangulated meshes. The software itself has got its own built-in intelligence where it can generate the right kind of meshes. You will not find any kind of unwanted hotspots or anything coming of that area. Next one is, the GPU acceleration. Actually, we should not be talking about this because it's the underlying hardware solution that we are talking about, which, as an engineer, we should not be worried about. We should be having a good infrastructure which takes care of the backend process. But these days, as you are aware of, if you want to do an iterative modeling, modeling when it comes to the hydrodynamic analysis, it's pretty fast. You just change your load case, you get the answer immediately. But when you move to CFD or FE analysis, which is more related to, infinite, lot of measures, every iteration will take a lot of time. So to take a decision itself, it's going to take a lot of time, and then you will not be able to take any decision because of the time constraint. That's where, these kind of concepts are coming up, where, the analysis which used to take days is taking only hours, and then you can definitely concentrate on analyzing your results than the actual process of doing your analysis. Next one is, DNV SESAM. This is a class society specific software. Of course, when you go to this offshore analysis, for example, offshore, the wind is a dominating factor. So when the wind load acts on the software platform, it obviously changes its heel. which again changes the hydrostatics, then that means, I mean, your mooring loads are different. If the vessel is shifting to one side, I mean, you are having more weight on one side, and then, I mean, more tension on one of the. So these kind of things is like, I mean, a multidisciplinary approach where it is required. So you have, I mean, softwares like, I mean, GHS, which can take care of the windage area, but then there should be another, I mean, software which should be taking care of. So the analysis part when it comes to the riser tension at all. So it's basically, I mean, we have to ensure that the same data passes through. So when, as a student, I mean, you'll be thinking, when what's the big deal in passing the same data everywhere? It's one file. But obviously, I mean, the people who are sitting over here who are in the industry will be agreeing with me, saying that, I mean, it's always a case of data management. There is a disconnect engineering group who does the analysis. And once you do the analysis, even your analysis model is gone. And then once you move on to production, for example, I mean, I had in one of my earlier projects, I mean, the longitudinal bending, and the shear stresses were exceeding, and they had to put some additional thickness, or I mean, additional walls over there. The structure people, when they're doing the structural, it's an empty area. I mean, you can put how much ever bulkheads you want. I mean, nobody cares about that. But when it goes to real production, when you talk about your when you talk about your arrangement of machineries and all, you cannot have I mean, you cannot have a bulkhead in the center of your engine. I mean, just giving a crude example, nothing like that happened. But that's where, I mean, the focus of multidisciplinary things are coming. So obviously, when it moves on to production, they'll be having their own practical issues. They'll change it. But is that change getting reflected back to the design? No. And if at all the design comes to know that, I mean, there is a change that the production has put into force for practical issues, do you think that, I mean, they're going to do a reanalysis, submit it to class? It's going to be a vicious circle. I mean, so that end-to-end approach is not happening, and that's what I'm trying to highlight over here with this integrated approach. So again, I think I touched upon Maxf and Moses already. I mean, Maxf, these kind of, I'm just connecting, though it's a structure-related thing, I'm just connecting the hydrostatic aspect, because the approach for the software is a little different. Because when it comes to Maxf, you are having a final equilibrium concept where even if there is a damage case, it knows, considering all your damage and what is the kind of cross-threading that is happening, it will finally gives an equilibrium position which takes care of everything in a minute fraction of a second. But when you have to analyze this particular aspect in your structure, this particular aspect has to be taken over there, then you should be having your non-linear analysis where you have to do your fracture mechanics will come into play, where you have to analyze your structure again with the kind of damages that has come to your vessel, and then again the probability matters over there. So that's where, I mean, the integration comes. And I think GHS, the wind display, I mentioned about that. Like, these are softwares which can really take care of the 3D structure, and then analyze the wind structure with the wind load that is coming on that. And again, FastSub ship, I'm just putting over there because it's just a legacy tool for NURBS modeling, which do not really come into the purview of analysis. I'm skipping that. So now, I mean, these are the new softwares. I'm not saying, I mean, these are the kind of solutions you should be looking forward for, but these are in the right direction, I would say. For example, of late, I mean, this particular software, TTM, that's from Korea, that caught my attention, because they are having as an integrated project which has got the capabilities of doing your initial structural design, which takes the same model is taken all the way down to the production line. So any change, I mean, since these Koreans, I mean, their design house and their shipyard interact quite frequently, and they are in good communication. So always they get a timely feedback. So whenever the feedback comes from production, they make the changes in the same model, which is again reflected back in the initial design. So as a initial structural designer, you will also get an idea about what is coming over there, why this particular change has happened. This will help you understand what is the reality of the production, and then you have to make changes accordingly. And like what Girish mentioned earlier, I mean, sometimes, I mean, to some people, I mean, it doesn't make any difference between 20 plate and 25 plate. So many of the times it depends on the logic. Depends on the logistics of the shipyard. Sometimes shipyard will say, okay, we have got 25 plate over here, so it's just a bracket. I mean, why don't we put, I mean, 25 plate in front of 20? We also think like, I mean, no, yeah, it's just a bracket. It's not going to make much of a change in your entire weight or anything like that. So it's being approved. But I've seen one particular aspect where, I mean, we were working on FPSO. We were having one modules tool which was having a bracket. So as you are aware of, I mean, there is a lot of interdependency where your hull girder bending will affect your topside modules. The stresses will be induced over there. And then there is an operational load that is coming from the topside, which is coming down to your hull structure. So the interfacing point matters. That's where you try to soften your contacts, try to reduce your hotspot so that your fatigue loading doesn't come over there. So that's where you put in the brackets. So in this particular case, what happened was that, I mean, the production approved, I mean, a thicker bracket, but finally when it went for reiteration, we found that, I mean, that particular thick bracket with a hard toe was creating a hotspot over there. So then again, it's a fatigue problem over there. So from a fatigue perspective, they wanted to reduce the thickness of the bracket back to whatever they wanted to, but then the production had already taken the liberty of taking whatever buffer they had and they got it approved. So that's where the integrated approach comes over there. And Catmatic is specifically just a production engineering tool. So, but again, the advantage of that one is that it's a lightweight model where people can work from different areas and like different geographies. And always, I mean, there is multidisciplinary. Like electrical people, they want to put an opening in your hull structure. It's again back reflected to your hull structure. So that direction is correct, but they don't have an analysis capability. Napa again, I mean, Napa is having a wonderful, I mean, as much as the softwares I've seen for naval architects, I feel like Napa has got a very good model where you got a single database which is connected to all your calculation. And nowadays they're having something called as Napa Steel, which is helping um, put the structure also in place. So everything is in a single model. So that's where the industry is heading to, as much as I would see that. And this is again with regards to rule compliance. For example, I mean, I'll not take into detail, but if I'm talking about DNV, you are having DNV 2D Nauticus, and then you are having a DNV Genie program where it's pretty simple. You are defining your midship section over there, and you are giving the thickness, and the same data is connected to your Genie. So that means your FE model is linked over here. There is no mismatch going to happen. Point number two, you can always pass this model to the classification society directly. That, I mean, they can also work on the same model, and then you are got you should be ideally you should be getting the same results. So talking about the future of analysis, I mean, AI is the buzzword. Again, I mean, we are all as engineers, we have to make calculated judgment. That's not where AI is going to help, but definitely there are areas like, I mean, improving your mesh, I mean, giving faster output. For example, I mean, you are having multiple variants of the same vessels. You have done a lot of analysis, and then you want to make a small change. Again, you cannot afford to make another 3-4 days of running of the analysis, and then you cannot afford to wait for that result. That's where AI can do a lot of data management. I mean, these days there is a lot of AI ML models available, like artificial intelligence and machine learning, which makes you give an initial prediction. So when you have to give your final output, definitely you'll have to take your traditional way. Your final design, whatever you come up with, whatever is conclusive, I mean, you should be doing that analysis on top of that. Next one is a digital twin. These days, I mean, digital twinning is like, I mean, the production engineering, as probably Sivaprasad sir, since I taught you, I mean, it's like a jigsaw puzzle kind of thing. You have your entire structure in place, you cut it down to blocks, and then you bring it down to the smallest part. Then you build up that parts using the drawings that you're making. But then, as I told you, I mean, there is a lot of challenges which you face in shop floor, that you face in production floor. For example, you're building, I mean, even including your A, or it will be giving you areas which are not accessible. So then they make changes that has been reflected back. So digital twin these days, it's not like, I mean, you're doing a scanning and taking a digital twin. It's like, it's a continuous live model. It means it lives for the entire life cycle of the asset, right from your initial design till the time you, I mean, probably you finish with your recycling. You have to make changes in the digital twin. So these inputs should come from your surveys. There are timely surveys that is happening. Whenever you make changes in the yard, that has been reflected over there. So it requires a lot of discipline, and it requires a lot of change in the approach for having an integrated area where, I mean, all the domains are contributing. That's where the integrated compliance is coming, where you got the CAD and then rule check. Now, it's not like, I mean, somebody creates a 2D design, another person does the analysis. So I'm just reiterating the same part. So design versus reality, again, I mean, you can always have a FE model which is nice and good, but in reality, I mean, there are a lot of human factors, like, I mean, insulation tolerances are there. For example, recently we did one hatch cover analysis, but finally we found that it was not opening properly. But it's again like, I mean, there is a lot of mismanagement in the way they put the hinges, but that is not never thought about when you make the model, because the computer will give you a very clean print. So you also have to always have to think about those aspects, given adequate buffers over there. And then all your environment model and, I mean, and unpredictability that is coming over there, then your entire service life you have to think about. It's not like you just give a corrosion margin. You have to understand where the corrosion is happening, how the structure is going to change over years. And again, operation limit from analysis is like, I mean, we always take a static case. I mean, when we do, we will not be considering the exact C conditions. Of course, I mean, these days we are taking the spectrum we are taking and that we are imposing over there. And again, for maintenance and planning integration, these days there is a lot of ERP system because the entire vessel or an asset is being considered as a plant, and then you have got your entire changes that is happening is being reflected in one place. You have an ERP system which will again internally can tell like, okay, one particular part is degraded, or you have a preventive maintenance system which tells you, okay, this particular part may wear and tear, I mean, in particular time, then you can advance order that. So it's all integrated in one place. So as I told you, I mean, I'll not take much time in the coming slides. So we have a single model problem where the technical team and the operation team, all of them contribute their information. It's all coming to one single area. And again, the design of a team and the field realities must be understood between each other. Like, I mean, you cannot expect, like, I mean, somebody working on the ship, they make a change, they make a drawing and give it to you. So that has to be understood. There should be systems in place to have the model completely in sync with the reality. And then operational feedback loop. This is something which, I mean, obviously through your organization discipline only you can bring it on over here. So yeah, this is with respect to shipyard operations. I mean, these are areas where, I mean, you have to think about, obviously, this is where the costs come in place. You can have the best of all systems. You can couple your CFD and FEA. Then you have to think about what is the kind of infrastructure you have to put in place. What is the amount of time? So should we go for an overkill or should we go for the essential things? That is a question you have to address when you go for a shipyard perspective thinking, because there it always is like, I mean, time is money. So you have to think about the best solution. I mean, whatever is practical within the reasonable time frame without going, I mean, polishing your output too much with no real requirement. So I think I more or less I covered this perspective, like, I mean, regulatory compliance. I mean, how we liaise the designer himself liaise with the class and how it is changing, and how the hull degradation has to be captured using your strain gauges. These days, I mean, there are a lot of mechanism by which, I mean, you can get the real-time stresses that is acting, how much cycles of load is coming. Then you can use that for predicting your fatigue. Then how the human factors are intervening and what has to be the benchmarking, and how do you handle the predictive maintenance. I think with that I conclude, and thank you for your time.
Thank you, Anish, for that presentation. So next, I'll invite Mr. Nishu Kurup, Principal Engineering Advisor, Naval, for the presentation.
Good morning. Can everybody hear me? Okay, perfect. So this is actually the first time, the second time I'm coming to this department. I've never been in this department, but I feel I've been here because when I was in Houston, most of my friends were from Houston, and they all tell me stories about what's happening, how they had fun in Houston. And let me tell you, those guys had a lot of fun. I don't know whether you guys are having so much fun, but it's good to be here. I basically used to work, my background is in offshore engineering. I used to work in Houston for 17 years. And I just returned back there and I just joined Naval, which is basically a boat company. As some of you might, I think most of you might know about Naval. And basically I joined Naval as the principal engineering advisor to extend their capabilities to offshore and marine engineering analysis. Extend the capabilities of that. So this is actually not really a good picture for the title out there, because it shows it's an FRP boat. It shows one of our boats out there. So let me just. Okay, so what I will do is I'll just go over some of the projects I have done when I was in Houston, and these are basically offshore projects. So this is one of the projects we did in 2011. That what you see is the WindFloat 1. It is the first offshore floating wind turbine on a semi-submersible. It was basically commissioned in 2011. And I think the font is too small, but it was 2 megawatt. It was basically like a pilot project it was one of the first projects, and The story basically goes, there's this group of guys from Berkeley. And they used to have this platform called Minifloat, and I was actually involved. It was actually supposed to be an oil and gas platform, and I was the riser engineer for that project actually. And somehow along the line, they decided that they don't want to do oil and gas, and they decided to remove the risers, put up like a shaft up there, put a wind turbine on the top, and they transformed it into a wind turbine. And it was one of the first projects, so there was a lot of challenges. There was no codes at that point. I mean, this is 2011. We are talking about very, very early in the offshore wind uh, um, avenue, and basically you had to use offshore oil and gas codes, which were very conservative, because oil and gas codes are inherently highly conservative. You are dealing with hydrocarbons. Something goes wrong, this oil in the water. You might have heard about the BP incident during in the Gulf of Mexico, Deepwater Horizon. Basically, they had an issue out there in some time back. So this is very, very dangerous. And offshore wind, of course, does not have that issue. There's no hydrocarbons out there. So the codes are, but you are using offshore oil codes, so you need to sort of change the codes. And there was a lot of challenges out there. And basically, the 3 pontoons, and this was installed off the coast of Portugal. It was a 2 megawatt plant, and in 2011, and I was working on this. So I was the lead fatigue analyst for this. And essentially, this is actually not really a good slide to show because there's too many words out there, but I'll just quickly go over how do you do a fatigue analysis. And I'll just go over it on a broad basis in the industry. So first of all, you identify the critical fatigue sensitive area. And you basically, that comes from engineering judgment. For example, in the previous model, the bottom of the tower is somewhere where you will have a lot of stresses out there. And you also try to find out what is causing the fatigue, what cycles are, is it the wave, is it the wind? And usually in the wind turbine, it's usually the wind that is fatigue driven. But in this particular, I'm sort of writing this in a general way so that, this is basically written for wave fatigue also. And then you do the hydrodynamic analysis. So you create a panel model of the body up to the free surface. You use a hydrodynamics potential solver to obtain the hydrodynamic pressure, which is basically pi omega j beta k, which what that basically tells you, it's that the pressure on a panel due to a unit wave that has a frequency of omega j, and it's coming from a director of beta k. So it's basically an array of, excuse me. It is basically a response to a unit wave out there and also the initial forces. And then you basically do it for all wave directions and for a certain amount of frequencies, the wave 3 seconds to 28 seconds out there. And next, what you do is the structural FE analysis, and then you analyze the global coarseness, and you basically do the pressure mapping, and that is the tricky part. So, what usually you do is use the same, you basically mesh the model in ANSYS, and you import like using panel model. When I say panel model, I mean quadrilateral elements, not triangular elements. Most of all the hydrodynamic frequency domain hydrodynamic software basically use quads. And you basically mesh it in ANSYS, and then you remove just the outer mesh of the of the vessel or whatever the floating body. You import it into VAMIT so that you have basically the same, the outer mesh is basically the same for both the structural as well as the hydrodynamic, so that you can sort of map the loads properly. So essentially you have the pressure arrays, and then you run ANSYS. Basically what you do is, in a fatigue analysis, you need to do a time series, but we actually do a trick. And basically the reason we can do this trick is it's a linear static analysis. Essentially, the structure is linear static. The only non-linear part is essentially the mooring lines, but we don't model the mooring lines. We just put forces or put like linear springs out there. So the reason we can, and the advantage of doing this is you can actually do one static analysis. And basically what you need to do is you need to find the stress points due to a unit loading. And then you take it outside, you find that out, you take it outside, and then you apply the actual time series. And since you have a linear analysis, you can actually do principle of superposition, and you can actually do the whole analysis outside in Excel or MATLAB. And you just need to do like the single the fatigue analysis, so like the structural fatigue analysis, you can just do a static analysis. This only applies if it's a linear problem. If this becomes non-linear, for example, if you're analyzing risers, which are like, it has geometric non-linearity, or if you have materials like a rubber or something, it's not going to work. All right, and then once you do this, once you get the analysis RAOs, then you need to pick an SN curve. And the SN curve essentially that it gives you the number of cycles with the stress curve. And you need to choose one either for the weld as well as the best fit. The key thing is the weld. I mean, that's where the fatigue is calculated. And you have different curves like DNVC curve, DNVB curve, and usually, and what you choose is usually a client. I mean, depends on the client most of the time, but usually a rule of thumb is base metal, you go for like the DNVB curve. Weld, you go for the COD curve. So, and these curves are basically they're sort of like bilinear lines. You can see them. Then you get the wave scatter diagram, which is essentially the you have your significant wave for HS, the peak period, and the probability that each of these combinations appear in your waves, in your wave spectrum. So you have the wave scatter diagram. Then you generate random waves from the spectra, essentially, and what you do for each HS and TP, you can basically generate random waves. And what you do is the key thing, one of the key things is you have a phase, you need to randomize the phase also, basically. So you basically take your phase from 0 to 2 pi, and you get a uniform random model out there and randomize it. And then you can get the stress time series. But what you have is, you have the RAOs for a unit wave. Now, once you have the time series of the wave, you can basically just multiply it out, and you can actually get the stress time series. You can actually get it outside of ANSYS. And then the standard way of doing fatigue analysis, you do rainflow counting, basically trying to find the number of the stress levels for number of cycles for each stress level. And there's a standard procedure for that. And then you use minus rule to get damage, and you can get your fatigue. So this is basically the fatigue analysis process actually. And the key thing out here is that you need to use, I mean, don't, for example, if you're going to do the fatigue, don't jump and say, I need to do the time series analysis in ANSYS, and that's going to take like a long time. You can maybe, if you are clever, you can actually take shortcuts. You can actually just do like maybe one static analysis, and then use that numbers and actually do your calculation outside, which save you a lot of time. Because if you're going to run a fatigue analysis for like the time series fatigue analysis for the scatter diagram, that's like a lot of runs. Okay, and especially, and of course, for the wind turbines, the number of load cases is like humongous. I mean, compared to, because you have that extra wind part compared to like oil and gas platforms. So you have a lot of load cases, like thousand plus load cases actually. Luckily, what we did not have so many load cases because we were doing it for the first time. We did not have any codes to follow. So basically, we just did the oil and gas load cases, and we got a little bit lucky that way. So this is one of the projects that I did, and okay, so I'm going to talk a little bit about quality assurance, actually. So this is another project that we did. I'm not going to name anybody in this project, basically. This is a horn mountain truss bar. It's basically a truss bar in the Gulf of Mexico, water depth of 5,400 feet. And it's basically been installed. It was installed a long time back. And we recently, like last year, we had a problem where what they wanted to do is they wanted to add a water injection line. They want to add a new riser and increase the topside capacity. So basically, the total weight, you're putting more weight or pulling down on the spar. So to compensate, you need to put a upward force, and what you do is you add a buoyancy cap, like which adds basically buoyancy to the whole system. So, and you can see this is a truss bar actually. This is okay. So you can see this. This is the process actually. You can see this is a truss bar. You can see the heave plates basically, which helps with the heave. And this is the center well. This is where the risers and all go down. Basically, it's like all the TTRs, top tension risers. And you have the buoyancy can is also kept in this way. So let me just get to the name. All right. So basically, this is how it looks. So we can see out here, this is actually what you see out here, this is actually the buoyancy can. There are like guides which basically hold it in place, lower guide, middle guide, upper guide. And they have variable ballast, you have a fixed ballast out there, and this is air. And basically you design the buoyancy can so that it can give enough upward force that will match the extra downward force due to the riser. So what happened is the company, the operator decided to give it to a very well-known company. I'm not naming any company, to do the FE analysis. And this is basically their model. I'm not sure I'm supposed to get this up, but I thought, okay, well, I will take a risk out here. So this is actually their model out there. This is what you see in the center out here. You can see all these slots. These are risers. There are risers that go through. There are also buoyancy cans. You can also put buoyancy. And you can see here they have put they have modeled it like in a very fine mesh, actually. And then they came for third-party verification. Now, third-party verification is something that is done in the offshore, oil and gas industry, because it's, as I said before, it's a very dangerous thing. So you always do a third-party verification. So they came to us, and my boss, the moment he saw the report, and he said, this is wrong. Okay, now my boss is one of the most brilliant people. Is an MIT PhD, and he's probably one of the most brilliant engineers. In fact, he actually he came up with the SPAR design. Is this the SPAR concept? He was the one who could prove it. So he saw it and he immediately said, so I can't do that. I will be very honest, actually. I mean, if I look at it, I will say maybe something is wrong, but he could say, look at it and it's wrong. And how do we do a check? Now we can do the FEA analysis actually completely like this, but that is not really the smart way to do. Okay. What you do is, what he did is, you put a stick model out there instead of for the buoyancy can, just like a beam model, very simple beam model. You can see out here. And he actually did this thing in Excel actually. And he basically, and the key idea you have to see is that if you're looking at it doesn't matter how you're modeling the buoyancy can. You could model it with beams, you could model it with shell elements, you could model it with solid elements. At the end of the day, when you cut a section, the moment has to be the same. That is not going to change. Okay. Now, of course, there's going to be, if you have solid elements, you are going to have extra geometric. You will have extra stresses due to the geometry and all that kind of stuff, and also the shell elements will have produced. But at the end of the day, when you make a cut and you integrate over the section, you are basically you have to get the same as the beam. I mean, that basically comes from the equilibrium, the dynamic, what you call conservation of linear momentum. And that is one of the fundamental concepts in mechanics. So what we, instead of doing all this, we just did a stick model actually, and he did it in Excel actually, and I did it in Orcaflex. So what you see, this is actually an Orcaflex model, and what you see, that yellow line is actually the buoyancy can. And what we found out was, when we did the moment that in the FE model was 10 times higher than our moment, which means that it is way off. So one of the key things, now I'm not trying to make the point that we were much better than them. Okay, these mistakes can happen to anyone. I could also make the same mistake. And I have made my share of mistakes. Some of them are a bit too silly to say here also. Maybe another time. But the key thing is, like, even though I might make the same mistake, I will probably catch it, because my mentors and my bosses always told me to do a proper QA. You need to do a QA for any FE analysis. And basically the idea is, however complex your model is, try to reduce it to like a something that is a closed form solution. You are not looking for an exact answer, obviously. You might not, you're not getting it, but you're looking for what's known as a ballpark, or like an approximate number out there. So if you have like a complex problem like this, and let's say your beam model is within 20 to 30%, then that's good. If it is 2 times, well, maybe that is also fine actually, because maybe you are not capturing all the effects in your beam model. But I would advise you to check the model. If it's 10 times, you're way out wrong. And basically, this is actually a very complex problem, because there is what you see in that thing out here, that blue in here. the blue, that's the moon pool, and the moon pool dynamics is very, very complicated actually. So they got basically they got the forces wrong, and we did more what is known as Morrison loading. So it's a very simple equation out there. And when they did they got the inertial loads wrong, and they were like they do make a mistake. And as I said, mistakes is going to happen. Okay, in engineering, mistakes always happen. In fact, sometimes I think that the Murphy's law was probably an engineer. So he was like, if anything can go wrong, it will. Probably he was an engineer, because there's something. Usually, you are going to make mistakes, but you need to make sure how are you going to recover from this. Do you have a backup plan? So every time you get a problem, you need, instead of jumping into the finite element, you need to understand the boundary value problem. You need to understand what the forces are. Try to make like a simple, like a stick model, or like a plate, like a very simple drawing, and try to figure out what the forces are, how is the body going to move. I mean, what is going to really happen out there? What really understand the boundary value problem out there before you do your FE analysis. And then because FE analysis essentially it is, it's a numerical model for the complexity, that is to deal with the complexity out there. And if you don't, model, it's like what they always say, like garbage in, garbage out. So basically, the QA procedures are very, very important. You need to have a good QA procedure always. You need to have something like, you always need to check your model, and this is also the reason why, closed form solutions are knowing your closed form solutions are very important, because, those are the ones that you can actually use for checking. So this is actually a general, it's probably, I'm not sure if the font is too small, but this is a general checklist that we usually use. So you have model, objective, global strength, geometry, materials, what kind of elements you use, element size and shape, what kind of boundary conditions that you use. So this is like a general checklist. Okay, this is a specification for a FES specification for a plumb analysis. This is basically a pipe line end manifold on the seabed. So that what you see out there, it's actually a pipe manifold. So that's a pipe that comes from the top. And I was actually asked to do an analysis. And you sort of prepare the FES spec first, actually, usually, and you say what are you going to do, like what is the element types you're going to use, what is the element size, the size that you're going to, what's the material properties, what's the loads, any special procedures, what is the quality assurance that you're going to do. So you sort of have this FES spec out there. And when you're doing this, again, it was a complex model. I mean, when you're going to model something like this, you don't need to model everything. I mean, we want to do a solid mesh at the key points, but you don't want to model the whole thing in solid. So you need to figure out where do you want to do the solid mesh, and then you need to figure out where do you want to do the shell mesh. You need to ensure that the transference of loads between the solids and shells are done properly. All the moments and all are properly transferred. Then you have the very bottom, you have beam elements. You need to make sure that the transition from shell to beam is also done properly. You need to make sure that all the moments are properly transferred. And so there are a lot of concepts out here that you need to be careful. The first step is always write up a FES specification, which you can actually also show the client, and make sure that he signs off on it. Okay, so this is another global closed style. So there's like a lot of special procedures, and I just put it out. It's probably like too much information. So for the next time, we're going to talk about parametric modeling. I'm not sure if I'm going over time out here. So this was something like an Arctic gravity brace structure we did for Shell. And this is for like, so it's essentially, it's like now it's like in 147 feet of water, I think. It's called a chukchi. It never materialized because the costing was too high. And so this was an ANSYS model. And what we did now, ANSYS, as you know, has, I mean, you might know, has, what you see at the bottom left out there is the workbench. But there is also something known as the classic, ANSYS classic, like the old timers like me, we will know, like that's what you see. It's called the APDL model. That's what you see on the top, oops, sorry. This one out here, that is basically the ANSYS classic. And the ANSYS workbench, that is actually mostly for multi-physics. It's actually, I mean, honestly, I don't like it that much because it's sort of like there's a lot of, you need to put all those modules in for each part, or for each, for meshing unit, for modeling, you need to add modules and so I'm sort of like I use the classic model. So because you have almost everything that you need to do in a FE analysis in the tree out there. You can start from scratch, do your modeling, and better, if you look here, there's a command line and you can actually write, there's something called ANSYS parametric APDL development language, which is basically like a Fortran based language. You can actually write down code to create your FE mesh. For example, this is actually for a differential structure. This is not the same thing as before. And you can actually write down codes like this. And these are all, and you can actually do the complete analysis like this thing. If you, I'm not sure if you can see this, but you have the first step, you define your parameters. Second step, you define your element types. Then you define your sections, and then your geometric modeling, your meshing, your boundary conditions and loads. Then you do the solution, like at the very bottom of your step 7, you see solution solved. And then you can do your post processing out there. You can type the view and you can save the images as a bitmap. Again, you will do a new analysis. So something like this is very useful. I mean, the advantage of doing something like this is that you can create a parametric model. So for example, this model, I mean, it has like a certain, width, and I can change like the diameter of the bottom part. I can change the diameter of the top part, and I just need to click a switch, and basically it just gets generated again. So this is now the APDL, the classic version is actually an older version, and it's not something that they recommend. I mean, they just have it for like old timers like us. The workbench, you can also do similar things in workbench using Python, and maybe you can use the help of ChatGPT or something to create your Python code, and you can also create. So this is something that would be interest for when you're so you should, when you're doing FEA, it's always good to have an idea about a language, knowing how to modify your code without clicking, or modify a model without clicking on it, is have a way to do that. It's always useful to have something like that, because you can actually, I mean, a lot of cases, I mean, I once did like a wind turbine FEA analysis like this, and basically they came to me and say, okay, one of the parameters have changed, and instead of having to model the whole thing, I just had to change a parameter in my script, and I could generate the whole model from scratch. So that is something that is quite useful when you do ANSYS modeling. Okay, and then, okay, one more thing about engineering judgment. So this is actually for this is a more node TLP. So TLP is a tension leg platform. They have tendons which are station keeping. So you have these tendons that hold it in place, and basically, they act as a station keeping thing. And this is like a tendon anode analysis. So for cathodic protection, you put sacrificial anode, and it's basically a very simple problem. You have what you see out here this is the tendon flange, and you have this anode which is basically welded to this side out here, and you can see this is the anode out here. And essentially, so we are basically modeling this in ANSYS, and you can now because I mean, I'm not sure if you can see the numbers, but the maximum number out here is 518, 520. So what you get is the tension in the tendon pipe operating condition is like some newtons, which corresponds to a normal axial stress of 183 megapascal. The maximum one Miser stress is a 520 megapascal. That is high. Okay, that is high. So for example, this particular thing, I think the one Misers or like the yield stress for like 360 or 400, something like that. Now it is high, but are you okay with that? I mean, you still, so the point out here is sometimes, even though you might have some amount of exceedance, you might still be able to pass it if you can get your logic right. So for example, in this particular case, if you see this, the red is actually at this very corner out here. And so there's going to be like local yielding is probably going to be there, but there's going to be, now this is a linear static analysis that we did. Okay, and now when I say linear static analysis, it means that there's no like there's no plasticity involved. So we just did a linear analysis. And so the thing is, like, once it goes into, if you're doing like a plastic analysis, once it goes into plasticity, it stays on the plastic. So it stays at, if it's like, not rate independent plasticity, it's going to stay at the yield stress. It's not going to exceed the yield stress. It's going to stay, and that part is going to flow, actually. But in this particular case, you can see that it is at the very much corner out there, and we sort of figured out like and the key thing here is that, this is whether the primary stresses, which is basically the stresses due to the beam theory, like MC over I, those are known as the primary stresses, whether the primary stresses get exceeded. If the primary stresses get exceeded, you're going to have catastrophic failure. If the secondary stresses, which are due to the geometric imperfections and all that case exceeded, you still might be able to pass it. So in this particular case, there was, even if local yielding due to redistribution, it is not expected to result in catastrophe. Analysis performed is linear, so the stress distribution is expected to be more conservative, because it's really, you are not the plasticity, as I said before. In plasticity, you are not going to see actually 520 megapascals out there. Still going to be a 340, but the thing is going to flow. Additionally, we modeled it without a no slip condition between the anode and tendon. So it acts as a conservationism in the analysis. So basically, this is actually an engineering judgment that you have to make. Like, a lot of times, sometimes you are not able to solve the problem. Like, I could actually, try to solve this problem, try to put like a bigger, but the question is it worth it? Okay, and if you are able to make an engineering judgment, and this comes from like a little bit of experience, you can see that, you can basically pass this model off. I mean, you can actually convince the client. You basically need to convince the client that, this is actually fine, And sometimes, even like I was doing a riser analysis once, and there was a compressive stresses at the bottom. And basically then, and that risers are extremely tough to, design, because it's just a pipe essentially. So, I mean, here and all, you can actually add structures, but if you're having like a pipe, there's only so much. You can only change the wall thickness, you can change the diameter. There's nothing much you can change. I was having compressive stresses, but I was able to, convince the client, like, we did some tests, so actually statistical tests, and we were able to convince the client that it is not going to be a problem. Okay, so you need to provide sound reasons if you are going to accept a design, even after design violations. You, as an engineer, you do have the power to do that, actually. So don't just be, tied, okay, it's going to violate, we need to cut off the design. It might be fine, actually. And in a lot of cases, the engineering analysis, actually, what you look at is like the boundary conditions. In the reality, in the analysis, boundary conditions are fixed boundary condition. In reality, it's not really going to be fixed. There's going to be a little bit of give and take out there. So, you need to understand that there might be a little bit of, leeway out there. So you need to also take that into account. So lastly, let me just talk about a little bit of learning FEA actually out there. So, I mean, how do you learn FEA? Now, of course, you can take a class, but the key thing is, understanding the concepts out there. And so one way that I look at it is, this is actually from my notes that I teach my engineers at Naval. So the key thing is, choose a very simple problem, like one of the simplest problem, and apply the concept to it, and do a hand calculation on it. So for example, springs in series. Okay, and now when you're talking springs in series, we are talking about the axial bar problem. The axial bar, if you take an axial bar, it just acts like a spring. It's, the stiffness is EA by L. So you can actually look at the springs in series, like take 3 springs. And for example, out here, you can get the element stiffness matrix. I'm just going to go through fast. And out here, you can construct the global stiffness matrix. So you can actually shows how to do and you need to like do this by hand. Like for 3 elements, you can actually do it for hand. It's like a 4x4 matrix out there. You can actually do it for hand. And then you can solve the global equation. and then do a 3-element axial bulb problem by hand using FEA techniques. And this is actually the best way to really understand, because since it's a very simple problem, you are not confused about like the physics. Actually, you can concentrate on the concept, FEA concept being applied, and what are the key concepts, like the Gauss integration, and also the shape function. How do they work? And the whole point is that whatever is applied here, what is the same for all structures. If you up for a 3D axial bar, the concept is the same for beams. So also the same for plates. Only the number of degrees of freedom changes, the dimensions changes. But conceptually, there is not going to be any difference out there. So you understand the concept for a very simple. One of my professors used to call do the problem for a little boundary value problem, which is like the simplest boundary value problem. Try to understand that first, and then you can sort of, once you understand that, understand the concept, then you can sort of like extrapolate to the higher thing. So these are like a list of design codes out there. So, and I think this is the last slide, but let me just quickly, I don't know if I have enough time out there, but let me just quickly couple of things. When Anish was talking about some futuristic things, I thought I should also probably make some comments out there on the what is the future. So first of all, LLMs are the big thing out here, like ChatGPT, and and I'm going to go in a little bit more, not talk about FEA, but trying to talk about like physics, because FEA is essentially you're trying to solve a PDE, like a partial differential equation. So like LLMs, the key point, like when you're trying to solve this, the major issue is the second word. It's like large language. So the problem is, like, for example, if you're trying to solve like a pendulum, and I tell you, like right now, I tell you one of the terms is mgl sine theta. When I say this mgl sine theta to you, you all understand, okay, m is mass, g is gravity, l is length, sine theta is the trigonometry, like the trigonometric function. For LLMs, mgl sine theta is mgl sin, then the letter delta. It is just a set of letters which is in a specific order, and they do like tokenization, and they have like positional tokenization, relative tokenization. Then they move it to an encoder and decoder, and they have multi-held attention and all that kind of feed-forward neural networks and all. But at the end of the thing, there's no physics out there. And that is one of the key things in the physics. And when you're talking about physics, the key thing is you need to have conservation laws. And that is one of the most important thing that you have to, because you have no, you might, and the thing is, if you do actually in ChatGPT try to solve the pendulum problem, it will give you the right answer. It's going to give you even the double pendulum problem, it's going to give you the right answer. But there is no guarantee that things are not going to blow up. That's the problem. That's one of the advantages of FEA, because FEA is essentially, we are talking about, it is essentially discretization of the energy. So you are basically, that is one of advantage compared to finite difference, which is when you're trying to discretize the differential equation. In FEA, you're trying to discretize the integral equation, which is like the much of the weak form, and basically that sort of ensures that your energy is sort of like stable. So that's one of the problems with LLMs, and one thing that I think in Anish's presentation I saw something called as a physics informed this thing. So that's actually a pretty new area. I don't have it slide for it. I probably should have. And it was basically started in 2017 by the Karniadakis group at Brown. That's known as physics informed neural networks. The idea is pretty straightforward. Like the neural network essentially is like a universal approximation. I mean, you put an elephant out there, the neural network will approximate it with like, there is no physics out there, there is no conservation laws. So what they did is, like in the neural network, when you're doing the analysis, you have something as a loss function, and you need to minimize it. So what they did is they put the energy as the loss function, and then you minimize it. So basically what's happening is when you're doing the calculation, you are automatically minimizing the energy. So essentially your conservation, you are basically putting in the physics comes inside the thing. This is known as physics informed neural networks. And this is mostly in the academia now. There is some codes out there, mostly in, I think Julia, some codes Also, NVIDIA has some codes out there that, but it's mostly in the academia right now. It is not yet come into the industry. I mean, I've not seen anything. I think like, and it's side showed it's like answers. I probably need to check up the latest answers, whether they have put it there. So it is basically, and mostly it is for fluid mechanics, and they try to solve Navier-Stokes equation or Burger's equation or something like that. So this is basically like probably what is the one of the latest state of the art, what might be coming forward. You don't never know whether, because at the end of the day, you need to have something that is better than FEA. That FEA actually is very well used and covers a lot of problems. And this particular area is you are just looking at some very specific, very academic kind of problems which are much more simpler, and we sort of need to, it needs to get to like you be able to solve industrial problems with it. So this is basically, I think this is basically all I have to talk. I might have taken up a bit too much time, but yeah, thank you for your attention, and I again appreciate the department for calling me for this panel discussion. Thank you.
Thank you, Mr. Nishu. So the last speaker we have for this panel discussion is Ms. Amla Sebastian. She is Manager FEA at Smart Engineering and Design Solutions, and has been handling final element analysis for both defense and commercial projects. So over to you.
Good morning, all. I think I'm audible. So first of all, thanks to the students for coming on a Saturday morning, especially on a vacation day. And now into the topic, advanced analysis methods and marine design and modeling. I've been working with smart engineering and design solutions for the last 9 years, ever since I left this institution as a postgraduate. And so I'll be talking about some projects and studies that we have been carrying out at SETS. So into the presentation. So these are some of the pioneer projects, deliveries, and works we have been carrying out throughout the last 2 decades. So coming to advanced simulations, there are mainly 4 areas: fluid dynamics, acoustics, solid mechanics, and electromagnetics, of which solid mechanics is my area of interest. So these are some of the advanced simulation services that we provide at SETS. Now straight into structural analysis. So let me talk something basic. When we analyze a structure, we have got mainly 3 methods: the analytical method, the experimental method, and the numerical method. So analytical method we use exact fundamental equations, mathematical equations, and get exact solutions. But this can be done only for simpler models and simple lots. When it comes to complex geometries or nonlinear behaviors, you cannot no longer rely on analytical methods. So next we have the experimental method. It is nothing but physical testing of the actual structure or some scaled down models. Here we can take care of these complex geometries, the nonlinear material behaviors. All this can be taken care of. But the thing is that it is time consuming and highly costly, as in factory acceptance tests, site acceptance tests, etc. So now comes the numerical methods. In numerical methods, they give approximate solutions or nearly exact solutions. But the thing is that we can go for complex structures. We can go for nonlinear behaviors. So these complex structures are broken down into smaller parts or elements, and these equations are solved for each of these elements. And we get a solution in lesser time and cost effective as compared to the experimental methods. So that is the main factor or the main driving force for the analysis using finite element method, or that is how this finite element sector has become or has got its glory and glamour in this marine industry. So these are some of the domains where we expertise at sets. The figure shows the vibration analysis results for a power swivel. Now coming to the global and local analysis. The figures show some of the full ship models. For full ship analysis, we had carried out for different vessels. So this full ship analysis is required for optimizing the design or to make the vessels seaworthy. And in full ship analysis, there are different methods carried out: extreme strength analysis, residual strength analysis, then buckling checks are carried out, and three-hold analysis for bulk carriers are carried out. So in extreme strength analysis, we load the vessel for the dominant load cases, along with the accelerations, and the wave effects are also included. And then we check for the yield criteria, buckling criteria, buckling for stiffened panels, non-stiffened panels, or roll panels, or all those can be carried out. There are tools like DNV pulse. And then there is residual strength analysis, where we check for the reserve strength of the vessel once some damage happens to the hull structure. So after the, so we remove a part from the vessel hull along with the main structures and check for the, we do the full ship analysis with a lower sea state or a lower wave height and get the results and check whether the reserve strength is okay. Now this is fatigue analysis. This is the figure shows the fatigue analysis done for some critical areas or the well connections in way of water jet duct at the transom area of a vessel. And here we use minor PAM grade method. It's an empirical method. And we find the damage factor based on the number of cycles to failure using the Nielsen curve. Now this is shock resistance analysis. This is a comparison between the static shock analysis and the dynamic transient time domain analysis. The figure shows the analysis done on a seating for a torpedo launcher. So the first figure shows the results from a dynamic transient analysis, and the second figure shows the results from a static analysis. So in the dynamic analysis, what is done is that the input shock pulse as per the rule or the INBR 3021 is applied on the shell where the below the shell where the explosion occurs. So the input shock wave is applied on the shell and the pulse propagates upwards and reach the seating and the structure beneath it in the case of dynamic analysis. And in the case of static analysis, we are applying this shock load as a static load at the COG of the equipment, and the stress gets or the impact is directly acting on the seating and the structure beneath. So you can see that in these two results, for the dynamic analysis case, the stresses are low as compared to the static analysis. So in this case, we find that the static analysis over predicts the stresses. So that cause to keep the stresses within the criteria limits, we have to increase the scan links much more as compared to the dynamic analysis. So that leads to a drastic weight increase. Also, you can see that sorry. So also you can see a hotspot stress in the dynamic analysis results, but not in the static analysis results. So you can see that actually there is a shape change. So that should be a hotspot area, but that is not resulted in the static results. So we can see that static analysis can misguide high stress locations also. So in this comparison, we find that dynamic analysis is to be done when it comes to shock analysis. So these are results for some of the special studies we had carried out. And there is lifting analysis. We do lifting and turning analysis for blocks at the yard. And there is the second one is normal free vibration analysis results for a piezoelectric transducer. And then the right top one is fatigue analysis results for a shaft generator for an LNG carrier. And then there is this fatigue analysis done for a tanker FPSO. Now, impedance and acoustic radiation. So impedance, by impedance, we mean to minimize the vibration effects that is transferred to the hull beneath. So when we design equipments, the design equipment seatings, it should be such that the seating, the equipment should be seated on a heavy girder so that this vibrations get attenuated as it reaches the hull, and thus minimizing the noise that is transferred to the water beneath. Now, ONTIX and ARIX. Underwater shock analysis. So the first figure shows the study done to know the impact of a underwater explosion happening beneath the sea hull, how the shock waves are transferred to the hull, and how the hull gets damaged. And that was done using Altair radios. Now, talking about comfort and habitability. So we have specific requirements in the rules for the comfort and habitability of the passengers and crew on board the vessel. So we will be doing full ship analysis, full ship vibration analysis with free vibration and frequency dependent analysis, frequency response analysis, and get the results in terms of velocities, output velocities, and we ensure these output velocities are well within the limits as specified by the rule. So in the figure, in the graph, you can see that the velocity outputs at different knots were tabulated, and these are to be within the limits. So this criteria are for different areas in the vessel. For crew accommodation area, we have a limit for the velocity. For the workspaces, there is another limit like that. So we make sure that these output velocities are within those limits. Now coming to weapons and sensors. So these are the seatings of the foundations for these weapons are to be handled much more different from those for normal equipments like compressors. Because in this case of weapons, there are two aspects, structural aspects and the accuracy aspects. So the structure should be strong enough and the accuracy should not be affected. So if you are considering the case of a gun, after each firing, the platform or the interface that is connected to should come back to the original or the deformations or the disturbances that has occurred should attenuate within a few milliseconds, so that during next firing, that should not affect the hit probability or the accuracy of the gun. So in this case of designing seatings or structures for the weapons and sensors, more care has to be given. And in the case of structural aspects, we apply recoil forces and moments, then get the results stresses and make sure these are within the yield criteria and buckling criteria. Shock loading is carried out. Missile blast, the blast pressure in the nearby areas, it will be applied and make sure that the area is safe. Then there is vibration aspects. We'll check for the free vibration and find and make sure that the vibration modes in the nearby area are not causing any resonance with main equipments. Then fatigue analysis whenever needed. And now coming to accuracy, we check for the angular displacement results and the dynamic amplifications that is taking place. So with the angular displacement should be such that the disturbances should attenuate within few milliseconds after firing, so that by the next firing, the hit probability should not be affected. And in the case of amplification, there will be some criteria for the amplification, dynamic amplification factors for the disturbances that is possible. So you have to make sure that these amplifications remain within the limits. And motion compensation, this power spectrum density of vessel motions. So what is the power spectrum density of the response of the vessel in areas, in the parts of in the areas where these guns are equipped? So at these areas, we check for the spectral density of vessel motions, mainly velocities and accelerations, and make sure these velocities and accelerations are within the limits that is specified by the maker of the gun. So, and then in case of sensors, we go for EMI, EMC, and flow noises. So that is with the different analysis and studies we carry out at SETS. And apart from this, there are several advanced techniques on developments taking part in the industry. As Mr. Anish has told, there are machine learning techniques happening, and there are these reduced order models, which are just surrogate models or black box models, which simplifies complex structures and gives results in within no time. So, and there are softwares like SimSolid, where meshing is not required. We can directly analyze the surface or the geometry and get the results. So there are different and much more advanced techniques happening. So dear students, please be upskilled and get ready for the industry. Thank you. Jai Hind.
Thank you. Thank you very much for the presentation. So now the floor is open for questions. So we are ready to take questions from the audience.
Good morning. It was all different types of presentations. I thought somebody would be doing the same thing, duplication will be there, but nothing happened, like duplication was not happened. It's very interesting. I have a question to Giri. You have the retrofit, whatever it is, and new design. So what do you feel the difference when you do a structural analysis for a new design and a retrofit or a repair? Is it the same conceptual platform is there, or you have a different conceptual platform because already existing one, and you don't have any freedom to alter that. You have to fit into that. So what is the conceptual difference between a new design analysis and a repair analysis?
Yeah, okay. We do both ways because we have requirements to start with the new one. New one, we have, as you said, there is a flexibility because we have the option to decide or we have the option to change it. The concept is same, of course, the design concept is same, the analysis method is same. When it comes to retrofit, the problem or the restriction what we face is mostly we get details from the clients. Drawings will be there, but the problem is the accuracy of the drawings what we get is sometimes in question. For example, if we have to analyze a barge where we need to install an equipment, maybe the plate thickness, maybe they have mentioned, let's say 15 mm, 16 mm, but actually it may not be because the barge may be in operation for 10, 15 years. So we need to have a UT gauging where we analyze the thickness, various thickness. But again, the problem again is we cannot have a uniform plate thickness in the analysis model. So we have to go for a case where maybe the worst case scenario where we can take the lowest thickness as a throughout the plate and then we do the analysis. So these kind of problems we face, but there we cannot have an accurate and we don't, mostly the problem is, of course, when you work with industry, the requirement comes today and they want the results yesterday. So there we have to compromise a lot, and I think all my panelists will agree with me. So we, in those situations, we play safe, to be frank. And the modifications also, sometimes we get an requirement that you want to install a David or an A-frame on the deck, and I don't want to do any under-deck stiffening because I don't have the time to do that. I don't have the budget. So we have to see how we can put that item on the deck without compromising the strength of the under-deck stiffness. Of course, there are methods we do that, and sometimes we have to play some kind of adjustments we do. But yes, for a retrofit, for a modifications, as a designer, we are not free to do as we do. But for a new concept, that's much more easy in that way that we can have a much better or optimized structure compared to a retrofit. Retrofit will be more of over designed to satisfy the client and the time. Thank you.
Yeah, I just agree to Girish. Like from an industry perspective, there is a lot of challenges. Like he rightly mentioned, one is lack of data. We never get the right kind of data, and whatever they are supplied, once we finish the analysis, we give it to class. They may be having past record. Still says no, this is not matching. But at the same time, if you ask the class, do you have the information with you? Can you release it? Sorry, the answer is no. So that is one challenge what we are facing. But recently we had one project where the client had to put a riser pouch on a platform. So our engineers, they did a perfect job. They submitted to class. We got approval. Then one fine, the client is calling me and asking, Anish, we just wanted to have a simple auto rickshaw. And then you are giving us something kind of a BMW, which means, they don't want that kind of a heavy structure over there. They just want to optimize. And another thing is they already have got items in the inventory and they want to use that inventory, but they'll never tell you on day one. You finish it, you give it to them, they'll say, no, this is not what we want. So you have to keep assuming. So that is the commercial issue that we face. And technically, when you are doing a particular kind of a retrofit, obviously you have to consider you are going to do the retrofit and you're going to put it on existing structure which has already undergone a lot of stress cycles. So you never have an idea about what is the residual life left in that particular area. So that approach is probably missing over there. That's my take on that.
Yeah, thank you. Any other questions?
Hi, this is Vivek from SETS. My question is to Mr. Nishu. So you showed one pilot project of a wind turbine. So of a turbine, right? A pilot project. So was it a composite structure? And it was steel. Okay, okay. That was just my thing. Have you worked on composite structures on this? Okay, okay. Even the blades that you showed were steel or what?
Yeah, okay, so, I don't work on the turbines actually. Turbine is a completely different area. So, I work on the aerodynamics of the turbine. So the turbine, of course, it's a composite structure and it basically is, it's like a lightweight and it's got like the aerofoil shape. But, we don't really, work on the turbine itself because when the turbine or the OEM also always gives us like a operating envelope. So as long as we are within that operating envelope, we are good actually. So from a naval architecture or like from offshore engineering viewpoint, it is the platform that is what we are worried about, like platform and the mooring and and the structure, basically the bottom of the tower. Essentially that is essentially our sort of scope. So the turbine itself is not really, we take the forces from the turbine actually. This in aerodynamics, you use blade element method and you get the forces from the turbine and you apply it to the nacelle and the tower. But that is basically our scope. So the turbine and yeah, those are basically the composites, but the structure essentially is steel, and there's also concrete structures. By the way, sometimes there is like they're putting in concrete spar structures. So I mean, it's usually steel or just because composites cannot really handle that. I mean, if you like if you're having like a wind turbine, you have the aerofoil shape. You can have a composites because you know the exactly how the wind is going to act on it. But for like a random waves and for a structure, it's composites is not really. It's not really a good material. I mean, it could lead to a lot of issues out there.
Any more questions? Ebenezer from this department. Very interesting talks, practical, and also you are willing to talk about problems you face, which many people in industry are not willing to acknowledge. It's a little bit late, so I'll start with Mr. Anish. You talked about a bracket and 20 mm, 25 mm, and how there could be fatigue failure in some places. So I was wondering whether in your process of design you do any kind of optimization for these structures, and whether there are multiple options which you are considered and then you finalize.
Yeah, this particular project which I spoke of was a kind of a new build FPSO, which do not happen normally because of normally most of the FPSOs are like conversion projects. So in this case, I mean, there is a lot of design iteration that happened, but ultimately after design iteration, I mean, there was some feedback that is coming from the yard where they increase the thickness. So from somebody who is thinking from a structural perspective, they'll be always be happy with more thickness. They'll be thinking, okay, this is good, I mean, let it be there. But there are certain areas where, I mean, there is a huge discontinuity is coming. For example, on top of the FPSO, you are having these module stools on top of which all these modules are coming. So these module stools will be like, I mean, like a hotspot which is creating over there. That's exactly where we had this problem. So we could do an optimized structure. We could clear the global analysis. Yet, I mean, when we come to local analysis of this particular bracket, we struggle, to be honest. So I haven't spent much time deeply. I don't know how they resolved it, but I clearly remember that, I mean, this was like a contradicting problem where strength aspect and fatigue aspect were acting in each other. But this number of brackets which were in question was very less, or the quantity was minimal compared to your entire cost or the size of the FPSO. That, I mean, people who are more aligned to production didn't care about that. So ultimately it was resolved. I mean, the class has to had to give a stamping on top of that.
Sorry, I have questions for all the speakers I heard. So, okay. So we had a case a few years ago where a boat builder made changes to the design. There was an accident, there was a court case, and eventually the builder went to jail and the designer escaped, very well-known designer, because he said you made it differently. So I'm surprised that in established industry, changes are made even if they are small from the drawings, and such things still happen during production. Just a comment. I'll move from that to the SN curve, which was discussed by Mr. Nishu Kurup. We know that if I want to design for a certain duration, some life, and if I can decrease my stress a little bit, my life will go up considerably. But when our MTech students go for a project elsewhere, the external guides tell you neglect the regions with high stress because that really doesn't happen. So they are told, oh, there is stress concentration here, but don't worry about it, go on. That stress concentration really doesn't happen. So how do you deal with it in industry when you are faced with stress concentration and you have to decide the life of your structure?
I mean, fatigue life basically is a cyclic phenomena. So essentially, you have looking at like you can have a low level stress for a very long life cycles that is actually going to take those things. Now, when it comes to stress concentration, the clear thing is it happening near a well? That is basic question that you need to know. I mean, that is the, maybe it's like the base metal, then that is fine. But if it's happening near a well, then you actually need to consider the stress concentration. You cannot go with the primary stresses. You need to, because that is the stress, that is the real stress that is happening in the world. And basically there is going to be like a cyclic loading with that stress concentration that needs to be taken care of. I mean, you cannot, just neglect it and say, I'm just going to use, MC over I as my equation, and the stress concentration does not happen. I mean, fatigue, I mean, there is going to be, what, if you don't want to ignore it, there's going to be a crack at the weld. That crack is going to happen, and your fatigue life basically is going to, go down essentially. So you have to model reality as it is, not what your version of reality is. So you have to always model, what is actually happening. So I mean, I would say that's very strange. I would say that they're just like trying to, because they were students, they're just trying to make it simpler or something. But in real, this thing, if you are trying to, do something like that, that will be a big red flag. I mean, it's like people will really question your competence actually.
You showed holes and you showed the stress concentration around the holes. How do you deal with that?
About those stress concentrations in way of the dynamic shock analysis, I showed the results. Yeah. Yes. Yeah, when there is a hotspot stress in the cost mesh model, we go for the fine meshing as per the role requirements, and then still we can see that if it is a real case scenario or real stresses, if those are real stresses, the hotspot stresses will be there after fine meshing also. So we will have to increase the thickness or increase the stiffness, add members. Yeah. No, we'll attend those stresses. We won't allow for this stresses unattended.
So you talked about whether really there. Sometimes it's very difficult to judge whether that's just a really difficult to that or it's an artifact of the information. And but you'll have to make a call, because if you can increase the stress by 10%, your life will increase considerably.
Yes.
So how do you go about managing this?
So if this, in some cases, this hotspot stresses will have to get the solutions by fatigue analysis. We'll have to run the fatigue analysis and reach the solution.
I think you're talking about probably singularities during the fatigue problem. That is what you're talking about. I mean, that is actually a theoretical thing, right? I mean, you are having an infinite thing at a hole out there. I mean, if you have like taking a crack propagation, then you start to need to look at fracture mechanics. You need to try to look at the J integral, and you need to sort of, instead of looking at from the point, you need to look. When it's new, then I mean, if you are finite element model, even after you refine the mesh, it shows a hotspot, then usually it will be there. I mean, the finite element analysis, most of the software, they are pretty robust out there, and they usually have, I mean, there's other things like numerical issues might be coming in, but once you are doing a mesh refinement, you can sort of, I mean, you probably need to do like a mesh convergence study out there to figure out whether it is real or not. And again, as I said before, I mean, like sometimes, even if there is a hotspot, if you can actually, justify it that there is not going to cause catastrophic collapse. So like, if it is going to be it's going to stay local and it is going to, just affect the plasticity along the hotspot for all design conditions. Okay, if you can do that, then basically you might be able to justify that particular hotspot. But you need to be a bit careful about that because, if you are going to exceed this thing, you need to document it out perfectly, and you need to tell what your summary about, like why are you making this judgment. So that it depends on the kind of problem that you are trying to solve. So it's like it's like there is the hotspots are there, but you sort of need to look at each problem differently, essentially.
Okay, I think we are a bit behind the schedule. I think the speakers will be available for a few minutes even after this. So if you want to have any questions, like you can have a chat with them after this. We need to wind up. Thank you so much for the presentations. We had 4 different presentations from 4 different perspectives, very interesting talks. Wish we had more time to interact. Apparently, the speakers have highlighted certain things which I think the students should have. I mean, the students might have got it. In fact, I had a comment for the students, but since most of the students are having their chai pe charcha outside, I'll reserve my comments. But I have a small question to the panelists because sometimes we get big question. I mean, sometimes we get requests from the industry to do certain problems. Okay, can you do this analysis and can you do this? Maybe it's CFDs, maybe it's FEM. But one of the challenges that we often faced when industry approaches us is like the time constraint. Like you want results in 1 week, 2 weeks, and this is not the way the academia works, because in 2 weeks we cannot do any meaningful work here because, like we said, whether it's FEA or CFD, we need to do all kinds of meshing and grid independent study or grid convergent study or whatever it may be, and it takes its own sweet time. But many a time the industry will be looking for answers within 1 or 2 weeks. So how do we, can you give us some, it's like, is there any advice on like how we can strike a balance between meeting the demand and accuracy? I mean, so something that we struggle with. Just quick, any quick answer to that? Don't have much time in 1 minute.
Actually, that question was already answered to Shivaprasad sir's question by Anish also. The industries works like that, especially when we work from countries like the Middle East. It's the last minute call, so it's not always we don't get time. And in the industry, yes, we have the option to keep the people working maybe overnight or weekends and all. But in academia, yes, I know there are issues, we cannot keep it. But certainly, yes, if there are requirements which allows us time, for example, like new building projects where we have time, then we can still consider involving the students also, because in other countries there is a good collaboration between the universities and the industries where they jointly develop some concepts, especially in the countries in Europe, and also those kind of collaborations are really, really a must. So, Steve, they're really serious with the industries. Yes, we are ready to, we are open to that. Even for the projects, for example, there can be a real-time projects where the students can be involved in our projects, where they can also get trained to the real projects. That's one option. Second option is where we feel there is time available. Yes, we can come to the department and get suitable students. But ultimately, what we find in the industry is that when the students come out from the academics, they are still not ready to accept challenges from the industry. So this way, where during the academics, if they can be involved in the real-time projects with the companies, they will be ready to go when they come out from the university. So we are welcome to wherever there is possibilities. Yes, we can do that.
Yeah, that's actually a very interesting question. I think a part of it is what is the depth required. I mean, academia is more depth oriented. I mean, you basically have a research outlook, and most of. I mean, if you're looking for a consulting project, most of the time you don't really need that kind of depth. So, I mean, there has to be a very clear understanding of what the scope is. Essentially, you need to define the scope because I mean, when I go to a professor, like, I work with professor at Texas A&M and also at MIT. And basically, like, we are very careful, like, and of course, the professors, I mean, their way of looking at things is like they have like this research outlook, what is new out there. And a lot of the times the industry goes there. I mean, there is something that's new, but most of it is old. And they are basically coming to you because you have that expertise of doing, like, you can do the old part much better than the other people. So then you sort of need to make sure that, like, I think you have to, like, maybe not go too deep into the research aspects and just like do the engineering side out there. And because I mean the time consuming wise, I mean, the two ways it time consuming, because I mean, if you're using students who are not very well knowledgeable, then there's going to be time consuming out there. But if it's like a consulting project, it is, you do have the knowledge. It's probably because you're trying to, go into that depth, asking questions that, maybe the industry does not really need to be answered. So it could be like, so yeah, this is the two things that I can think about.
Yeah, just adding one line over there. I mean, as we have spoken about, I mean, industry always values the time, and academia definitely values the quality. It's not that, I mean, the quality is absent from our side or you're not time bound, but there should be definitely some line between where that will only be known when we interact with each other. So we should be having more and more projects. And I would urge the students who are coming for internship to various companies. I mean, you try to find out what is happening in that company. I mean, what is the kind of project that is being undertaken, and then take some liberty to talk to the people, and then try to pull some work from there and bring it over here so that you can also get involved in that one. That will be the best way to, I mean, club the industry with academia, in my opinion. Thank you.
So thank you so much for your time. I would like to thank all the speakers who are here, who have taken time out of their busy schedule and came here all the way to share their experience, expertise in their areas. So really thank you on behalf of the organizers and the Department of Ship Technology. We are grateful to you for the time you have shared with us. Thank you so much. So we'll officially wind up this session. Um,
Thank you all. Let's now proceed with the certificate distribution session. Before winding up, I request Dr. D.D. Ebenezer to kindly present the certificate of appreciation to the esteemed panel members. I kindly request Mr. Girish Menon to receive the certificate. I request Mr. Anish Kumar Menon to receive the certificate. I invite Mr. Nishu Kuru to receive the certificate. May I request Ms. Amala Sebastian to receive the certificate of appreciation. Thank you, Dr. D.D. Ebenezer. I request Professor Dr. Shiv Prasad to kindly present the certificate of appreciation to the panel chair. Thank you all for taking the time to be with us today. A high tea has been arranged outside the seminar hall. Please do join and enjoy. Wishing you all a very good day. Thank you.